Greetings students, and welcome to our next lecture. Today we're talking about Laplace transforms of vector functions and how to solve systems of linear ODEs using the Laplace transform. Before we can start applying Laplace transform to systems, we need to figure out how Laplace transform applies to vector-valued functions. Fortunately for us, it's really not that hard, as the Laplace transform applies to each component of the vector individually. Before we start, let me say a few words about the notation that I use here. I use a little vector notation on top of the letters to signify that the quantity is a vector quantity. Your textbook may be using bold symbols or maybe using something else. There is really no universal notation on how to denote vectors in your mathematical calculations. So I'm opting for the easiest choice for a little arrow on the top so that we clearly know that this is a vector and we don't confuse it with scalar quantities or we don't confuse it with complex conjugation. So if you have a vector quantity and you want to compute the Laplace transform of it, then all you have to do is to apply transform of each one of the components. So it's going to be the Laplace transform of the component y1 of t, and the Laplace transform of a component of y2 of t, etc., etc., etc. So really applying Laplace transform to vector functions is no harder than applying Laplace transform to single functions. So this is simply a vector quantity that's comprised of y capital 1 of s, y2 of s, and all the way to yn of s. We're going to call it a vector quantity of Laplace transforms, vector capital Y of s. We also had quite a few theorems that talk about the Laplace transforms of the derivatives, moments, and shifts, etc. Pretty much all of this applies to the vector-valued functions without any change. So the Laplace transform of the derivative is going to be the Laplace transform applied to each derivative of each component, which is going to be s times capital Y1 of s minus the initial value at 0. So we can write it as s times the vector Laplace transform of my vector y minus the initial value of y at 0. And if we take the Laplace transform of a second order derivative, then we're going to get exactly the same result as in the case of one-dimensional functions. So it's going to be s squared times y of s minus s multiplied by the initial value of y minus the initial value of the derivative. In pretty much the same way the Laplace transform applies to antiderivatives. It's going to be 1 over s capital Y of s as a vector of Laplace transforms, multiplying by exponential factor. And I want to point out it's the same exponential factor for each one of the components of y. Doing so will result in overall shift of the Laplace transform. And shifting in the time domain leads to exponential multipliers in the Laplace transform domain. So this is going to be e to the minus alpha s. And this is a scalar quantity multiplied by a vector. Which means that every component of y of s is going to be multiplied by this exponential function. One thing that is characteristic for multidimensional vectors is that there are matrices that the vectors can be multiplied by. So if A is a constant matrix, then the Laplace transform of ay is going to be a times the Laplace transform of y. This is hardly surprising, as the Laplace transform is linear, and the multiplication by a matrix is a linear operation. So before we start looking at the systems of ordinary differential equations, let's look at a quick example of when we compute the Laplace transform of the derivative of this vector. And I want to do it several ways. I want to compute the derivative and then compute the Laplace transform, or use the relations we have for the Laplace transform. So the vector y prime of t is going to be the vector of minus 2 sine of 2t, 0, minus e to the minus t, and 1. And therefore the Laplace transform of it, of y prime, is going to be the Laplace transform of sine is 2 over s squared plus 4. Multiplied by negative 2 gives us negative 4 over s squared plus 4. Laplace transform of 0 is 0. Laplace transform of minus e to the minus t is minus 1 over s plus 1. And the Laplace transform of 1 is the Laplace transform of Heaviside function, so it's just 1 over s. Let's compute the Laplace transform with the relations we have in the previous page. If we compute the Laplace transform of y, then it's the Laplace transform of cosine of 2t, which is s over s squared plus 4. Laplace transform of 1 is 1 over s. And the Laplace transform of e to the minus t is 1 over s plus 1. And the Laplace transform of t is just 1 over s squared. Therefore, the Laplace transform of the derivative is going to be the Laplace transform multiplied by s. So it's going to be s squared over s squared plus 4, s over s in the second component, then s over s plus 1, and then finally s over s squared. And now what we have to do is we have to plug in t equals 0 into the function y and subtract from this function. Cosine of 0 is 1, so we subtract 1. 1 at 0 is 1, so we subtract 1 again. E to the minus t at 0 is 1, and t at 0 is 0. When we simplify, we get that this is equal minus 4 over s squared plus 4. S over s minus 1 is 0. And s minus s plus 1 is negative 1, so that's going to be the denominator here. And s over s squared minus 0 ends up being 1 over s. And we got exactly the same function for the Laplace transform of y prime. And this confirms the formula that we have on the previous page. At this point, having these formulas, we can apply this to the initial value problems with systems of ordinary differential equations. If we apply Laplace transform to this, then we get that the Laplace transform of y prime should be the same as the Laplace transform of a times y plus g of t. The Laplace transform of y prime turns into s times y of s minus the initial condition, which is y naught, and the Laplace transform of a times y is a times the Laplace transform of y plus what I should call it g of s which is the Laplace transform of g of t. Moving terms with y of s to one side and y naught to the other side, we get that s times y of s minus a times y of s should be equal to g of s plus the initial condition for y. You might be tempted to factor out y of s from the expression on the left, but we can't really do it as of now because s is a scalar and a is a matrix. And so we have to convert s times y of s into some sort of a matrix multiplication. And we can do it by multiplying y of s by the identity matrix multiplied by s. The result of this multiplication is the same. And only then we can factor out y of s. Because then, what we're going to have in parentheses is two similar sized matrices. Again, let's not forget that we can switch the positions of the matrices, as y of s is a vector and s minus a is a matrix, and the matrix multiplication is not commutative. And so far, everything looks okay. Because we have a vector quantity on the left and we have a similar sized vector quantity on the right. To figure out what y of s is, we have to use matrix algebra, and the matrix algebra suggests that we have to take g of s plus y naught and multiply them by the inverse of s times I minus a. And this matrix inversion may be a little bit tricky, but it's not something that you can't do. The matrices with the variables in them can be inverted in exactly the same way as you invert regular matrices with numbers. Having figured out the Laplace transform of y, we can now figure out the function y of t. That's going to be the inverse Laplace transform of si minus a inverted multiplied by g of s plus y naught. Let's look at a quick example. If you remember what you did in the differential equations class, then you found the eigenvalues and eigenvectors of this matrix. Then we found the fundamental set and the fundamental matrix. And then you used the variation of parameters formula with a big integral with lots of matrix products to figure out the particular solution. And after you've done so, you will have to solve the equations to figure out the constants. Laplace transform allows us to do it in a single swipe. It probably involves the same amount of work in terms of computations, but it's a cleaner approach. So let's see what we have. We get the Laplace transform of y prime, which is s times y of s minus 1, 2, should be equal to the matrix 5 minus 1, 3, 1, multiplied by the Laplace transform of y plus the Laplace transform of t in 1, which is 1 over s squared and 1 over s. Moving things to the other side, we get that y of s will be multiplied by s times the identity matrix of size 2 minus the matrix 5 minus 1 and 3, 1. That, when multiplied by y of s, should be the same as the vector on this side, which is 1 over s squared plus 1 and 1 over s plus 2. Let's simplify the right hand side. So it's going to be s squared plus 1 divided by s squared, and here it's going to be 2s plus 1 over s. So what we have to now do is we have to find the inverse of this matrix, which can be written as s minus 5, positive 1, negative 3, and s minus 1 times y of s should be equal to s squared plus 1 over s squared and 2s plus 1 over s. Now we need the inverse of this matrix. And if you remember how to invert 2 by 2 matrices, then you take the determinant of the matrix. In this case, it's going to be s minus 5 times s minus 1, which gives us s squared minus 6s plus 5 plus 3, multiplied by, we switch the main diagonal and negate the off-diagonal elements. So the top becomes s minus 1, 3, and s minus 5. Therefore, y of s equals 1 over s squared minus 6s plus 8 multiplied by s minus 1, 3, and s minus 5 is multiplied by the vector of the right hand side. The fraction can be factored out into 1 over s minus 2 times s minus 4. And let's go ahead and compute the matrix multiplication. We have s minus 1 multiplied by s squared plus 1 divided by s squared minus 2s plus 1 over s. And on the bottom we have 3s squared plus 1 over s squared plus s minus 5 times 2s plus 1 divided by s. At this point the computations become too cumbersome to deal with them by hand, and I'm going to use my favorite calculator, that is Mathematica. So let's first simplify the expressions in my vector. What we have is we have s minus 1 times s squared plus 1 divided by s squared minus 2s plus 1, and don't worry that I'm not using the signs correctly because I'm going to keep it as a single fraction. Now the second component was 3s squared plus 1 divided by s squared plus s minus 5 multiplied by 2s plus 1 divided by s. I'm going to use a simplify command to make these expressions a little bit simpler. Now this needs to be divided by 1 over, and the bottom is factored out into s minus 2, s minus 4. This might be too much to look at, but let's do the partial fraction decompositions for each one of those terms. So I can say that y of s must be a big vector, and what I'm going to do is I'm going to insert these expressions. Well, at this point it's quite easy to get the solution. We're just going to use the partial fraction decomposition to derive the solution. So we get 15 over 32 times e to the 4t. We'll also get 5 over 8 of e to the 2t. 1 over s squared belongs to the Laplace transform of t. and 3 over 32s becomes just a constant, or a Heaviside function. The same story with the second Laplace transform. I get 15 over 32 e to the 4t. I get 15 over 8 of e to the 2t. I get plus 3t over 8, and I get minus 11 over 32 of Heaviside functions. And if you're curious, you can plug it into the system above and verify that there's indeed a solution. Alright, so what we learned today is when we're dealing with systems of equations, we have to make sure that we're doing the matrix algebra properly. Also, the matrix algebra becomes quite involved pretty quickly. So most of the time we'll be using mathematical or similar tools to deal with these computations. The last thing I want to do is I want to take a look at the graphs of those equations in Mathematica. So all I need to do is I need to do inverse Laplace transform of this vector. And then plot these equations. And Mathematica is smart enough to figure out that I'm asking it to plot two equations on the same set of axes. So we're going to plot it for t values going from, say, 0 to, well, since I have exponential functions that are growing quite quickly, so I'm going to restrict it to a small interval of time. And this is what happens with these solutions. Both of the solutions go up pretty quickly. Alright, you may remember in your differential equations class, you have been told that any higher order system of differential equations can ultimately be converted into first order system, and therefore there is no need to study higher order systems. Nevertheless, Laplace transforms have an advantage that they can deal with higher order systems without converting them into first order systems. As an example, let's consider a coupled spring mass system, where on a frictionless surface, I have two objects of mass m1 and m2 connected by springs, and let's say this is the rest position. So if the spring mass system is in this position, it doesn't want to move. So let's call it an equilibrium state. If I perturb the system, let's say I move one mass to one side and another mass to another side, and let's call the perturbation from the equilibrium state y1 and y2. Then we can write a system of second order equations which will model the system. So from the Newton's law for the first equation, the acceleration of the first mass particle should be the same as the sum of the forces acting on this particle. And there are two forces acting. We have a spring with a constant K1 and a spring with a constant K2. The spring K1, when it's compressed, exerts the force that resists compression. So when y1 is negative, the force is positive. So therefore I get minus K1 times y1. The second spring is stretched, and the amount of stretching is y2 minus y1. And the force that wants to pull the spring into the positive direction. So it's going to be plus K2 times y2 minus y1. The second equation is going to be mass of the second particle times the acceleration of the second particle equals the sum of the forces acting on the second mass particle. And what we have is the spring K2 exerting the force, and this time the spring is stretched and it wants to move the particle to the negative side. So it's going to be minus K2 times Y2 minus Y1. And the spring K3 is compressed, and the compression is by amount Y2. And since the Y2 is positive, and the spring wants to move the particle in the negative direction, there's got to be a minus sign times K3 times Y2. This differential equation is going to apply to any possible configuration that the system might be. The only thing that we should be aware of is we shouldn't really try to model the system when the masses m1 and m2 switch their positions. If that happens, this model doesn't apply anymore. Let's just say that the vector y1 and y2 at t equals 0 equals y1 naught and y2 naught. And the vector of derivatives of y1 and y2 at time equals 0 would be equal to y1 naught prime and y2 naught prime. These are going to be just four numbers that are going to be predetermined before we start solving the problem. So if I want to write it as a system of second order equations, I really need to divide by m1 and m2, so that what I will have is some vector of y, second derivative, will be equal to some matrix times the vector y. The first component is multiplied by minus k1 over m1 minus k2 over m1. And the second component is multiplied by k2 over m1. In the second equation, the first component is multiplied by positive k1 over m2. And the second component is multiplied by minus k3 over m2 minus k2 over m2. And we can see there is certain symmetry to this equation. So if we apply Laplace transform, which is s squared times the vector of the Laplace transforms minus s multiplied by the initial condition minus the vector of initial derivatives should be equal to this matrix divided by m2 multiplied by the vector of Laplace transforms. Now let's join the like terms together. We get that y of s will be multiplied by this giant matrix. I have s squared plus k1 plus k2 over m1. Second component is going to be minus k2 over m1. On the bottom I have minus k2 over m2. And the last component is s squared plus k3 plus k2 over m2. This is what y of s is multiplied by. And this is going to be equal to s times y naught 0 plus y naught 0 prime. And on the bottom s times y2 naught plus y2 naught prime. Computing the inverse and multiplying these together will get us the Laplace transform of y, and then computing the inverse Laplace transform will give us the function. I don't want to do this by hand because it's so much easier to do it with Mathematica, and I already pre-computed everything. So here's the matrix A. The matrices in Mathematica are double lists. The first list is the first row of the matrix. The second list is the second row of the matrix, etc., etc. The vector B is computed as a double list too, because it's a matrix with two rows, and each one of the rows contains only one component. Then what I want to do is I want to replace the parameters k1, k2, m1, m2. y1, 0 is y1 naught. y1, 0p is y1, 0 prime. So I want to replace all of those with some numbers. I'm going to assume that the first element is quite light and the second is quite heavy. 6 times heavier. K1 is going to be a very stiff spring with a spring coefficient of 10. K2 and K3 will be very soft springs. Initial positions, I'm going to displace the first element by -1 unit, so I'm going to move it to the left by 1 unit. And the second particle is going to be moved by 2 units. So what else is going on here? Well, I compute the inverse of A and I multiply it by B. Matrix multiplication in Mathematica is the dot operation. Don't mix those up because the star operation is a termwise multiplication. In this regard, Mathematica is a little bit weird. It's done because the matrix multiplication works as a dot product, and hence the dot is used in Mathematica. So all I have to do right now is to compute the inverse Laplace transform of this result. And I get the following expressions. I get sines and cosines, but this is expected because we're going to expect a vibration in this system. What I want to do now is I want to make it a little bit pretty. So I made a little animation. I draw a line and I draw a red circle and a blue circle for the second mass component. I'm going to animate for the time interval from 0 to 20. If I evaluate this, I get this animation. And what we see is the first mass element oscillates quite quickly and the second mass element oscillates quite slowly. And this is expected because the second mass element was a lot heavier. If I want to change the parameters, all I have to do is to go up, change my parameters here, take this function, invert the Laplace transform, redefine y1 and y2, and then recompute this animation. Alright, going back to our theoretical material, the last thing I want to talk about is the topic of system transfer functions. Just like in the case of the one-dimensional initial value problems, the systems of ODEs generate their own transfer functions. We have seen it's done in the two examples before. So for the first order system, we have that S times y of S minus the initial conditions equals to matrix A times y of S plus the Laplace transform of the external forcing terms. So if the initial conditions are 0, and I mean 0 vector, that all components of the initial conditions are 0, I get that y of S can be written as a matrix multiplication of the inverse times the Laplace transform of the input. And therefore this matrix inverse is the system transfer function for the system of ODEs. For the second order ODEs that we considered, the system transfer function was the inverse of this matrix, right here. Let me write it in general. And again, I'm going to assume that the system was initially at rest. Which means all the initial conditions, all the initial derivatives are 0. We get that s squared times y of s will be equal to some matrix times y of s. That's the Laplace transform of the input. Because all of the initial conditions are 0, I don't have any extra terms on the left. And therefore y of s, after a bit of manipulations, becomes s squared times I minus a inverted times g of s. And this matrix inverse is going to be the system transfer function for the system of ODEs. And this is where we're going to end today. I hope you liked it, and I'll see you in the next video.